As we said, the most important representations of a group are the irreducible representations, because all representations are equivalent to direct sums of the irreducible representations. So let's look at how to construct irreducible representations of the symmetric group. This is usually done using Young tableau. So we'll define a Young tableau of shape lambda to be a Young diagram of shape lambda filled with non-negative integers. And we call the Young tableau standard. So if lambda is a partition of n, if it contains one through n, each letter exactly once, and increases in rows and columns. For example, the standard Young tableau of shapes lambda partition of 4 are, for 4 we have 1, 2, 3, 4. So that's the only way to put numbers in the tableau of shape 4. I guess we could draw the boxes here so that the numbers increase along the row and increase in columns. For 3, there's 3 ways to do it. 1 has to go here. We could put 2 above and then 3, 4. Or 3 above and 2, 4. Or 4 above and then 2 and 3. Sorry, this is 3, 1. For shape 2, 2, there's 2 ways to do it. 1 has to go here and then 2 can go above it or to the side. If it goes above, then 3 and 4 have to go in these positions. If it goes to the side, then 3 and 4 have to go in these positions. For shape 2, 1, 1, there are 3 again, and they're the transposes of these tableau. On the side we could put 2, and that forces 3 and 4 to go in order above it. Or we could put 3, and that forces 2 and 4 to go in order above it. Or we could put 4, and that forces us to write 1, 2, 3 here. And then there's one tableau of shape 1, 1, 1, 1 that's standard. It's the transpose of this tableau. Of course, if we want to increase in columns, we have no choice but to write the numbers in the order 1, 2, 3, 4. Sometimes f lambda, let me write that a little lower. F lambda is used to denote the number of standard Young tableau of shape lambda. And this is equal to the dimension of the irreducible representation of Sn indexed by lambda. Now there's infinitely many irreducible representations, because whenever we think of one irreducible representation, we can conjugate it by any invertible matrix that we want. So there's infinitely many because of the possibility of conjugating by an invertible. Well, if the matrices are f lambda by f lambda, then I guess that invertible matrix is going to have to be f lambda by f lambda also. But in spite of that, all of those possibilities, these all have the same character. And this is usually written chi lambda. So one way to produce an irreducible representation indexed by lambda, a partition of n, is to use a subspace, let's call it V lambda, of polynomials in n variables. And we want to produce matrices that are f lambda by f lambda. So if we have to pick a subspace that's that dimension, because the linear maps from that space to itself are going to be that size. And so if we pick a basis of the subspace, then we'll let the symmetric group act on that somehow by linear operators, and then we'll get matrices of these size. So now we want to have a basis which corresponds to standard Young tableau of shape lambda. So for each standard Young tableau SYT, let's say the standard Young tableau of U is U of shape lambda, we define a basis element, and let me call that basis element ZU. And ZU is the product over all indices, index pairs I and j, where j is greater than I, and I and j appear in the same column of U, the product of xj minus xi. Then the vector space that we want, V lambda, or maybe I'll put lambda above, is going to be the span of all these elements ZU, where U is a capital U, is a standard Young tableau of shape lambda. And then we let SI act on the space as the linear operator that swaps xi and xi plus 1. So for example, let's look at lambda 3, 1. So we have the 3 Young tableau, the 3 standard Young tableau, 1, 3, 4 on the bottom with 2 above, 1, 2, 4 on the bottom with 3 above, and 1, 2, 3 on the bottom with 4 above. And then, so each of these only have one column with 2 indices in it. So this is going to correspond to x2 minus x1, x3 minus x1 for this one, and then x4 minus x1 for the last one. Any column that has only one index in it doesn't contribute to this product of differences of variables. Now, when S1 acts on this one, we just get the opposite of it. When S1 acts on this, we get x3 minus x2, and when S1 acts on this last one, we get x4 minus x2. x3 minus x2 is x3 minus x1 minus x2 minus x1. So x3 minus x1 minus x2 minus x1, because then we'll get x3 minus x2, and the minus x1 will cancel with a positive x1. Similarly over here, this is x4 minus x1 minus x2 minus x1. Positive x1, negative x1 cancel, leaving us with x4 minus x2. And then, well, the matrix, let me keep this table here. I'll show how S2 acts, and then I'll do the matrices up there. So when S2 acts, we swap S2 and S3, so we get x3 minus x1 here, which already is a basis element. That's good. And here we get x2 minus x1, and then there's no x2s or x3s there, so we just leave that basis element as x4 minus x1. All right, and then the matrices. The matrix of S1 is, so the first basis element got mapped to negative itself plus 0 times the other two. The second basis element got mapped to itself minus the first basis element. And then the third basis element got mapped to itself minus the first basis element. So there's the matrix of S1. And the matrix of S2 is even simpler because the first basis element got mapped to the second. The second basis element got mapped to the first. And the third basis element got mapped to itself. So then, of course, we can multiply these matrices to get matrices for S1, S2, S2, S1, S1, S2, S1, and of course the identity element gets represented by the identity matrix. The end.